Did you ever know Ralph Beebe, who was professor of chemistry
I only
at
saw him.
Amherst College?
I saw him one time at a meeting. I
Yes,
didn't know him.
yes. He worked with H.S. Taylor, you know, in Princeton.
Yes.
And I met him at Bristol when I was doing research there after I got my first degree. For his sabbaticals, he liked to come to Bristol and work with my old prof, who was Professor W.E. Garner. One of the old school. We had a finger in all kinds of pies, you know. It wasn't a very narrow kind of chemist. He was an explosive expert as well, Garner, and so I had a lot to do with the theory of solids. So that was a great help in the catalyst area. But yes, BB was an awfully nice chap. I liked him very much, and I spent about 1.5 years with him, and then till the war was obviously coming, and I came back to England.
And during the war, what did you do?
Oh, I was working with Imperial Chemical Industries, of course. We were told what we had to do, and yes. Of course, I worked at first in research, and then I was catalyst plant manufacturer, manufacturing catalysts. So I have a sort of experience of every area of catalyst work, all the way from running catalysts, operating plants, to making catalysts and research. But most of my time has been in the latter part of my career as research. And mostly trying to find new catalytic processes in the days when people were even interested in finding new catalytic processes. Yes.
What did you do for your PhD?
I'm measuring the heats of the calorimetric measurement of heats of chemisorption. And that's what Prof. Beebe did, and that's what I did with Beebe at Amherst too. Studied the heats of chemisorption of gases on oxides, calorimetrically. Very interesting. Beebe and I found a thing which is really very interesting, which has never been pursued, though I know that someone in the Atomic Energy Authority found it with oxygen. It's not so surprising with oxygen. You know, he found that gases would go on into one state, and then they would move to another state. And first of all, their first heat was a low one, heat of chemisorption. And then as you waited, the heat would rise in the calorimeter. This wasn't an artifact, I mean, plenty of proof of that. And the absorbed gases, the whole monomer would change into another, more strongly held form. And of all things, I found that with nitrogen on Cr2O3. There's many things which require re-examination, you know, in the light of modern techniques. But, for instance, hardly anybody knows anything about the chemisorption of nitrogen on the lower transitional metal oxides. It turned up a bit recently in some of the lower titanium oxides, the reduced titanium oxides, but apart from that, nothing. However, that's another matter. Yes. And where were you then before you finished? I won't say you finished. Passed on to Kentucky and the institute there.
Oh, I was teaching in West Virginia. Before that, I was at Mobile.
Oh, you were with Mobile, were you?
Yes.
Yes. Were you in Weiss's time?
Yeah, he was there.
Is he still around?
He's at Penn State.
Oh, yeah, so I mean, he's still extant, as we might say.
Yes.
Good. Yes, I think about them a lot, but I don't really know any of the young catalyst people anywhere, and certainly not in the States any more than anywhere else, for that matter. Yeah.
Now, after the war, where did you go?
Well, I was first of all here at Billingham, and I was safety officer in the research department, and then towards halfway through the war, I went to the catalyst manufacturing plant at Clitheroe, which had to be kept going because we were making the catalyst to produce the high octane petrol for the Air Force. So it was all go in those days. There's no let up. But no, if you mean did I serve in the army? No, I didn't. No.
No, but afterwards you.
Well, I came back from the catalyst plant and then started developing the fundamental ideas I'd had before and during the war, when we couldn't do anything about it, you know.
Mm-hmm.
Michael Polanyi was one of our consultants at that time.
Oh.
And he was the first man I discussed my electronic theories of catalysis with. And in fact, he would have liked me to go on to work with him at Manchester during the war. Of course, I couldn't. And after the war, well, everything was different after the war.
Now he was still in science, even though he had switched to economics.
Yes,
But
well, I don't really remember. He became an economist and a sociologist and finally a philosopher.
yeah,
In fact, I got his book upstairs, which is called Personal Knowledge. It's very good. It's well worth reading. And nowadays, I've become very interested in philosophy. I go to Leeds University extramural lectures here in Middlesbrough, and I'm learning Latin in the same place, and I keep up my French and Spanish. I not speak either of them very well, but I can read and write them quite well. Mm.
Now, how did you get into the electronic theory?
Well, because I was at Bristol doing my PhD research at the great flowering of solid-state theory that happened in the middle 30s, the early and middle 30s. It was if I remember correctly, it was only in the early 30s that first gave the explanation of semiconduction in solids. And the school there was at, that'll be, what's his name? The School of Solid-State Physics and consequently chemistry, solid-state chemistry at Bristol. And that's of course where I tuned in on all that stuff. And but at that time, it wasn't until I got into industry and learned more about catalysts. You know, I'd only been studying chemisorption of simple gases, and but when I got into the industry and came in those days, we used to do every kind of catalyst chemistry here at Billingham, you see, not just one kind. I mean, latterly it just became methanol and ammonia, not much else. I mean, this is before modern times, before synetics and catalytical before that. We did every kind of reaction, inorganic and organic, catalytic, so we had to get a vast experience. And it was only because of that that my ideas clicked, because you could quite clearly see how things were behaving according to their position in the periodic table. And from there on, you could get on to molecular orbitals and all the rest, you know.
But how did you come to nickel copper?
How do we come to nickel copper?
Yes, as the one that you used.
Well, nickel anyway was widely used. I mean, it was a standard hydrogenation catalyst in those days. And but during the war, we were hydrogenating nitrobenzene to aniline. And of course, for that, you can either jiggery-pokery with the reaction variables and get selectivity, or you can use a 100% selective catalyst, although it's less active, and that's copper. Copper chromite. Believe it or not, Adkins copper chromite was pelleted and used in a fixed bed for hydrogenating nitrobenzene to aniline, and they built on the basis of their work and the semi-technical work, or what you would call pilot plant work, which was done at Billingham, they built, in the early days of the war, they built a plant over on the west side somewhere near Runcorn, I can't remember where. Oh, I mean, it was the difference between copper and nickel was so marked. It was still a bit of a mystery as to why it was active at all, copper, let's face it, but And of course then one related it to the electronic structure of solids, and in those days more particularly the density of states at the Fermi surface. And then predicted that there would be a minimum in the middle of the periodic table at manganese. And after that, some years after that, Dan Ely and another chap found it in a hydrogen-deuterium exchange. And from there on I said, well, why not, if metals, why not oxides? And it's the same with oxides. The activity falls as soon as you get beyond group 8, and there's a minimum in the middle at manganese oxide. And similarly with the sulfides then. But this is a theme that really needs examining, but nobody does it. Nobody does it anymore.
At this time, did you interact with Wolkenstein at all?
No. Well, one knew of him, of course. But he was very much took a very strongly physical view of Wolkenstein. It wasn't as useful as going into the molecular orbitals, which could tell you more about the chemistry.
And after you did the nickel copper work, what followed that?
Oh Lord, what followed that? Well, after that, we didn't do so much. Well, we didn't, strictly speaking, have the facilities to do fundamental work. That was our problem in those days. And so after playing on with the theoretical stuff for a while and trying to make a complete story of it, which I think we did, then I went on to exploratory catalytic chemistry, looking for new catalytic processes. I gave an example this morning. I was talking about hydrogen peroxide production and the in situ use of it. And and also we did some gas phase work. We oxidized formaldehyde to make reactions in the hydroxyl radicals in the gas phase, and use that to make phenol from benzene, but that was not catalytic, that was a purely gas phase oxidation. And after that, of course, we tried to oxidize methane to methanol over molybdenum containing catalysts. Well, it did, but the selectivity was only good at very poor conversions. This was years ago. This was about the time of the Russian International Congress of Catalysts. That's 68, isn't it, I think? Mm-hmm. And after that, we tried to make ammonia over some reduced molybdenum oxides at room temperature and pressure, following some work of Oskar Glemser in Germany. And we think we made it too. But again, we didn't at that time have the facility of using a mass spectrograph, so we couldn't do the most desirable proof using mass spectroscopy. We had to do it by using inert gases in splanks, but we still think we made small amounts of ammonia by bubbling nitrogen and hydrogen through the suspension aqueous solution of this stuff. Of course, it was industrially of no interest at all, because nobody wants aqueous solutions of ammonia, and anhydrous ammonia. But what one I had in mind was this business I spoke about this morning of going into a kind of imitation biocatalysis.
Oh, the sun is in here.
So then of course we did a lot of work in connection both with methanol and with steam reforming, and designed catalyst. We even suggested palladium catalyst for ethanol synthesis. And subsequently, in many later years, of course, people did use methanol and basic supports to make.
After the electronic theory, why didn't you go to university?
Well, I became then interested in using it to design catalysts. Instead of pursuing it as a purely theoretical exercise and doing calculations, I'm not a mathematician, so I didn't go too far into theoretical calculations. In any case, such calculations in those days anyway would have been so approximate as to be pretty useless. I preferred to use a semi-empirical quantum chemistry and draw conclusions about the way catalysts worked. And after that, I devised a system for catalyst design, which has never been published in complete form, but it exists in papers here and there. And of course, in connection with designing catalysts, then we entered in this exploratory catalytic chemistry, trying to find new processes, which I was telling you about, which I've told you a little bit about. What was I doing just before? I retired in '76, which is quite a while ago, and that was after methanol. Just after the big thing with methanol. I mean,
you mean the low temperature?
Methanol, yeah, copper catalyst methanol synthesis. And at that time, by then, of course, it was established as a process worldwide, I think. But by then, I'm getting a bit shaky on the exact dating of all this. But before this, of course, there was the steam reforming catalyst, and I wanted them to make a rhodium catalyst on magnesia alumina spinel, but because of course it's fantastically active in steam reforming. And it only needs minute amounts of rhodium, but as you can imagine, with all the as we were saying this morning about Fischer-Tropsch, with all the investment in nickel catalysts, nobody was ever going to turn over to a highly questionable catalyst, which was in principle very expensive to make. That was kind of how I went on. We devised methods before use of nitrous oxide for measuring metal surface areas. We developed a low temperature process for doing it by oxygen chemisorption, and showed that the activity of copper water gas shift catalysts were proportional to the area of the copper. We showed that very early on, actually. It was a long time ago now, that. A chap called Alvin Thurston worked with me with that, and published a paper in Transfer Stock about it, about that time, a long time ago.
How did you keep the scientific interest while you worked in industry?
Oh, well, I kept reading the literature and working on it in my own time, you know.
And after you retired, you stayed in?
I used to do, I did quite a lot of, I lectured at Hull University on solid state and on catalyst design based on solid state chemistry. At Hull and Imperial College, did 2 periods of visiting professor at Imperial College when Oberloda was there. And later, after Oberloda retired, I did it again. Then I went up to Edinburgh University and did some work on alumina with Charles Kemble for a couple of years, which was quite interesting, but nothing extraordinary. And then I did a lot of lecturing around and about for people at universities here and there. Oh, and I did a spell of helping a chap at Warwick University called Ashok Bhattacharya. Very curious setup. Never mind, we mustn't record this. I helped a chap there for a while. Yeah.
Well, those are the best kind of report.
I wouldn't like my unkind comments to get back.
Who did you work with while you were in industry and academic in England? Or?
Who did I work with in the universities?
Yes.
Well, we didn't do any work in those days with the universities. We did a bit, but not nearly as much as they've been doing latterly. We used to give Charles Kemble a lot of money to do his work, and you know the kind of work he was.
This was a deuterium.
Determining mechanism by deuterium exchanges and so forth and so on. And we were giving Charles Kemble a lot of money, even when he was at Queen's University in Belfast. And of course, we gave you know John Rooney at Belfast, you know, a brilliant chap in exploratory type work. And I used to act as a liaison with them, but I can't say I influenced their work in a great deal. But curiously enough, Wynne Roberts was at Queen's University before he went into the physical chemistry of catalysis, working. He came, I think, from one of the government laboratories. Yes, he did. He came from one of the government laboratories to work at Queen's University as a lecturer, I suppose, in the first place, until he went on from there to ultimately to be professor at Cardiff. And we gave John Pritchett at Queen Mary College a lot of money. He worked on copper. He did a lot of work on copper. Well, as you probably remember, he showed that hydrogen is in fact activated chemisorption of hydrogen on copper, though it's rather weakly held. So that helped to solve one of our early problems, that we couldn't understand why copper was a hydrogenation catalyst, since it apparently didn't chemisorb hydrogen. Well, he showed that if you looked at it carefully, it did. You know, and yes, I think I'm running out of details now.
What, in your view, helped establish England as a leader in catalysis during that period following the war?
Well, I think really, because in the universities primarily there are a lot of very able chemists like Dan Ely, Charles Campbell, or one-time pupils or chaps associated with Eric Rideal, and all well-known, powerful and skilled in surface chemistry. And their teams were very able. The people who worked with them were very able. And there was a general enthusiasm at the time for it, of course, in industry. And industry, ICI in particular, ladled out tons of money, really, to these people over the years. I think it happened to be a thing of importance at the time, put it that way. It happened to coincide with the boom, the discovery of deuterium and then the use of deuterium from the early 30s onwards into kinetics and so on. Well, I think that's about it. Who can account very often for the sudden burst in interest in a particular topic? It is certainly true then that the major chemistry-based industries like the oil industry and the heavy chemical industries like ICI and Shell and BP were very interested in catalysis and process in those days. In addition to which, of course, they nicked quite a lot of processes from the Germans who lost the war. And these had to be, were all being developed, and as they were developed, they generated more chemistry and more ideals and so forth and so on. But I feel sure if it hadn't been for the war, there would have been quite a lot of those German chemists who would have been Nobel Prize winners, you know. And then, of course, it was then not long after that, it was followed by Ziegler and the Ziegler-Natter polymerizations. And that took off again with another lot of kinds of catalysis in a kind of chemistry of which we had a lot of inorganic, metallo-organic chemists who knew a lot. I'm trying to think, what's his name, who worked at Imperial College on the carbonyls. Never mind, it's gone. I'm getting old, I'm afraid.
And what was your biggest frustration?
Well, I think one has to be honest here, and I have to say that it was principally because the management ceased to be interested in exploratory catalytic chemistry. That's it, fundamentally. And the universities don't do it, can't do it. Doesn't fit the examination system. I don't see why people can't do exploratory catalytic chemistry in universities. When they write, there's always this thing in PhD and other theses that you must produce publishable novel material. Well, suppose you gave a young chap the job of trying to find another way of making ammonia, and he worked very skillfully and well and brought everything to bear on it that he could, but was unsuccessful. But if he produced a good thesis, I would have thought it been worthy of a PhD. In other words, I can't see why PhD students at universities shouldn't do exploratory catalytic chemistry, even if though they're unlucky in the end in getting a novel process out of it. I've talked about this a lot with Win Roberts. He was keen to do it, but never, for the reasons I've given, able to introduce it. So industry doesn't do it, and the universities don't do it. So what's the answer? Well, there's nothing new in catalytic chemistry at the moment, is there? I don't think so.
What does...
I mean, really new, like a Ziegler-Natter catalysis, or even some new brilliant oxidation catalysts we don't have. I mean, that's almost routine now, oxidation catalysts, isn't it? With all the work that was done in the States and elsewhere on the what shall we call them, semiconducting oxides, but that's not their most important property.
Well, if you were going to pick areas to explore now, what in catalysis, what would they be?
Oh, would they be the ones that... Well, I can't name a particular process, but I can only say that I would pursue the sort of thing I was talking about this morning, where you make hydrogen peroxide, you don't separate it, you use it in situ. And, for instance, when we were talking about the Fischer-Tropsch this morning, or this afternoon rather, and I was talking about, well, why don't we go straight from the hydrocarbons and dehydrogenate them in situ and then use them immediately and polymerize them up to the things you want? Why not think about doing things like that? Entirely, not entirely new, but newish. I was very interested a few years ago with some French work. In fact, I'd done quite a bit of thinking about it myself, because I was wondering, why not just decompose your hydrocarbons and make carbides, and then hydrogenate your carbides to your hydrocarbons. And lo and behold, not long after that, some French people talked about doing just that. The problem would be, of course, to recover the hydrogen from the dehydrogenation step. However, that is perhaps a little outre at the moment. That would be a bit outre. But the idea is to make active intermediates, in essence, active molecules, and never isolate them, but use them inside you to add on or react in some ways, or insert or whatever into other molecules. I mean, for instance, you could make the hydrogen radical in the presence of formaldehyde. Well, another thing that interests me was what used to be called primitive earth chemistry, you know, in which if you stew up formaldehyde with ammonia long enough, you make imidazoles and things. Well, I tried to get a research project for that over at our local college, because at that time I was external examiner for their bachelor, their honours degree course. And they had some very able chaps over there who could do some research. They even had a man who knew all about imidazoles and things like that. So I got a grant from the Research Council for them, and they couldn't get anybody to come and do the work. Anyway, you know, that primitive earth chemistry, you see, is very interesting. If you go back a bit and imagine what you might do by combining things in situ as you make them. But this is very exploratory. Well, as I understand it, it's very exploratory, but I can't say that I'm now au fait with current catalytic chemistry. Oh, the only thing that I am familiar with, because of my early interest in it, is the production of hydrogen peroxide, which people are doing with these titanium-containing zeolites and other solids. They're doing some quite interesting oxidation work with those. But of course they use hydrogen peroxide or organic peroxides. Well, fine, that's all right, but it'd be much better if you didn't have to use hydrogen peroxide, but just made it in situ and used it. So, that's the sort of thing that I mean. Yeah. But,
where do you find the drive to continue to read the literature on catalysis?
Well, the short answer is that I don't, because I'm not reading the current Catholic literature. To be able to read it at all, I have to go to Durham University or go to Billingham. I've been invited to use the small library that they have at Billingham. But you see, the only way to do exploratory chemistry is to keep in touch with practically all chemistry. And that means, for instance, reading chemical abstracts, which I used to do. I mean, after all, it only comes out once a fortnight, the particular sections that interested. And I used to go through them, you know, and you pick up all kinds of odd bits and pieces and then try and put them together. That you have to keep clearly. You have to have a very broad interest in chemistry, organic, the lot, you know. And nowadays you have the added feature, of course, that there's an awful lot now of homogeneous catalytic chemistry about, which is also has to be included. Well, I don't think I have anything else to say.